Hi, and welcome to DNA replication. In eukaryotes, we start with double-stranded DNA. This is just a snapshot, a small part of a chromosome, which remember when we talked about has multiple origins of replication. The origin of replication will be abbreviated as ORI. Remember, there are lots of these across the chromosome, and the same thing happens at every single origin of replication. So we're going to zoom in on one origin and go through the basics of what the nucleotides look like for DNA replication. We will add and talk about the proteins more in the lecture, but this we're going to focus on what happens at the DNA level. So the first thing that happens is that the replication bubble opens at all of the origin of replications. We're going to just talk about one. So we can imagine, right, our replication bubble looking something like this, with our origin going down the middle. So let's zoom in on this guy and look at the polarity of the bubble. So I'm not going to finish the bubble because I don't want them to cross. So if we go with polarity, and by convention, the top strand will make 5' to 3', which makes the bottom strand automatically 3' to 5', because DNA in double strand is always anti-parallel. Again, here's our origin of replication. Now, we want to remember two basic rules when we talk about DNA replication. Number one is strands or complementary base pairing. The strands must be anti-parallel, right? So anti-parallel is one of the major rules, right? So maybe number one. Number two is polymerases and replication, or the addition of new nucleotides, must occur at the 3' end of the nucleotide, at the 3' OH. So must add to 3' ends only. Right? We can never add any nucleotide to the 5' end. The third rule is that polymerases doing replication, DNA polymerases that make more DNA, complementary base pair DNA, must add to an existing 3' end. They cannot add to naked DNA. So they must have an existing 3' end, a 3' OH to add to. So how the heck can they do this if we're looking at the replication bubble, right, with two different strands, right? The top strand here, right, which I'm going to overlay a little bit, okay, so that it looks blue, and the bottom strand. As it exists right now, this is naked DNA. So what has to happen is that a primer, or a small bunch of nucleotides needs to come and sit down. And as it turns out, these nucleotides are made of ribonucleic acids. They're ribonucleotides. It's a little chunk of RNA. So I'm going to show you what would happen if we put a little chunk of RNA, right, on all the sides of our origin of replication, right? Remember, going down the middle is our origin. And remember in class I said this is the no-fly zone. We cannot pass the origin. So if we place an RNA primer, denoted here in red, right, the RNA primer, again, another strand of nucleotides, must be anti-parallel. And so what we can see is, by convention, if this is the 5' end of the DNA strand, this end of the primer must be the 3' end, right? It has to be in order for it to be anti-parallel, which makes this the 5' end. In the same way, this end of this guy is the 5' end because it must be anti-parallel with that 3', and that makes this guy the 3' end. So again, 3' to 5' to be anti-parallel to our 5' here to 3' here strand. Okay? And in the same way, we want to set up our polarity of primers down here, right, to make sure that they're anti-parallel to the existing strand. And then we can look at now what can happen during DNA replication, right? Again, the polymerase must add to juicy 3' ends, the 3' OH. So the only possible way for complementary base pairing to occur in which direction is on the 3' ends, right? So this way is a 3' end, here's a 3' end, here's one, and here's one. But look, we cannot cross the no-fly zone here or here. And why can't we? Because there's another primer sitting right here. That red line that you're looking at is actually nucleotides, RNA, right? AGCUs sitting there. So we can't polymerize off the end of this guy, and we can't polymerize off the end of that guy because it's stuck to the other end of a primer. There's no place to go, right? It's already hydrogen bonded and complementary base paired to the templates, right? Remember, how do nucleotides stick together? A's, in this case, A's and U's, T's and A's, G's and C's, by hydrogen bonding. So the polymerization must occur only at the 3' end. So we can start adding, the DNA polymerase can start adding nucleotides to the 3' end of this RNA primer. That's RNA, 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 right? And we're complementary base pairing, right? Hydrogen bonds are forming between the complementary base pairs. Okay, so we can do that guy. We can do this guy. Here's another juicy 3' end, right? Going this way, we have hydrogen bonding occurring here. That's the complementary base pairing. And again, we can see that both of these yellow lines are going into the replication fork, which we lovingly refer to as the replication crotch. So what strand goes straight into the crotch without needing to stop or do anything else? Yes, replication fans, we call that guy the leading strand. So that guy's leading and this guy's leading. Okay, so then what the heck happens to the other strand? We cannot complementary base pair off of this 5' end. Polymerases just can't do it. We cannot use that 5' phosphate for squat. So what has to happen? What has to happen is that primers need to be set down away from the origin, not at the origin. So RNA primers will sit down away from the origin, right next to the crotch. Right? On the lagging strand, the primer sits at the crotch. And if you look at its polarity, now the 5' end is closest to the crotch, the 3' end's here, 5' end, 3' end. Why? Because they have to be anti-parallel. Now we can do some extension, some complementary base pairing, right? In the direction towards the origin. If a primer happened to sit at the origin, it's just going to sit there and not go anywhere. And the strand, the lagging strand, is going to bump up into whatever is sitting right next to it. So it'll go as far as it can and then stop. Go as far as it can and then stop. Okay? So if you want to look at this in a bigger picture so you can see a little bit more, this part of DNA replication we're going to show on a new slide. So let's look really quickly and let's draw the bubble ginormous, right? Let's say it way, way opened up like this. And here's the 5' and the 3', and here's the 3' and the 5'. Again, here's our origin of replication. And if we draw in our primers, right, here's the juicy 3' end. Okay, here's the juicy 3' end. In this case, we're going to draw a couple different primers on the lagging strand. Okay, and we'll draw in polymerase will go this way, bump up to the origin. Polymerase will go that way, bump up to the origin, doing complementary base pairing. Right, the leading strand's going to go right into the crotch and just keep going. That. The lagging strand has to stop and make a new primer as the bubble's opening. Right? Remember, crotches are opening in this direction and it continues to go. As it opens more, we add another primer next to the crotch and move back towards the origin. For the leading strand, as we open more, the leading strand just keeps following the crotch. Okay? And so that's how replication initiation and replication elongation happens. In the next educreation, we're going to talk about termination of replication and what happens. Because really, right, remember, all of this red stuff is RNA. We don't want RNA in our DNA, right? Our chromosomes are made up of double-stranded DNA. We need to get rid of the RNA and fill back in with DNA. and then connect all these tiny little pieces together. Okay, so that's replication, initiation, and elongation. Your next educreation will cover getting rid of those RNAs and the finish. So thanks for listening, and see you soon.